All right, welcome back. So today we're going to introduce notions of absolute and conditional convergence. A subtle notion, but a notion that based upon what we've seen to this point in the course in our study of series, we are ready for. So to sort of introduce these topics without explicitly defining them, let's talk about sort of a tale of two series, if you will. So one of the series is the alternating series minus 1 to the n over n squared, and the other is the alternating series minus 1 to the n over n. Now, if we look at both of these as alternating series, we could apply the alternating series test to each, and we could ask ourselves, well, in the one case, do the 1 over n squareds decrease? Yes, they do. Do the 1 over n squareds go to 0? Yes, they do. Well, hey, then by the alternating series test, we have convergence of this alternating series. So to see this explicitly, the series here, I believe, is what? Minus 1 plus a fourth minus a ninth, and so on, right? Yeah, what about the series minus 1 to the n? Well, let's look at that in its alternating series form. Take the minus 1 to the n out of it. Do the 1 over n's decrease? Yes, they do. Do the 1 over n's go to 0? Yes, they do. And as a result, this alternating series converges as well. So to look at this alternating series, this is what? Minus 1 plus a half, minus a third, and so on. So we've got our two alternating series sort of explicitly articulated, at least to a few terms. And yeah, we get convergence of both of these alternating series because, well, alternating series have an easier time of converging than their non-alternating counterparts, which is exactly what's going to come into play here. What if we remove the alternating nature of these series and consider its corresponding positive term series? So we are considering a different series than the original series now, but what if we just looked at the sum of the 1 over n squareds? Well, the sum of the 1 over n squareds, this would just be like 1 plus a fourth plus a ninth, and so on. This is 1 plus a fourth plus a ninth, and so on. Well, hey, that converges by the p-test, right? When you have just a power of n in the denominator and the power is greater than 1, you get convergence. That's the nature of the p-test. Well, what if we remove the alternating nature of the series of consideration on the right, considering the series sum 1 over n? Well, that's our classic harmonic series, which we know diverges. This is the sum 1 plus a half plus a third, and so on. And so this diverges. You could view it via the p-test. You could say that it's the harmonic series and diverges. But note, that is different behavior here, right? Because whereas the alternating series in both cases converged, when we looked at the corresponding positive term series, in one case we still maintained the convergence, whereas in the other case we didn't. And that's a little bit bizarre. And that suggests that while both of these alternating series are convergent, they're sort of convergent with less sensitivity in one case. You could turn all the terms positive and maintain convergence, and more sensitivity in the other case. As you start taking those negative signs and turning them positive, suddenly the series diverges. And so how can we capture the essence of the difference in the behavior between these two series? Well, let me pause the video and define. All right, so to take these two series and put into words the difference in behavior with them, both as alternating series converge, but each as non-alternating series looking at the positive term counterparts have different behavior, convergence in one case, divergence in the other. So here's the definitions we can follow. If the sum of the ANs converge and the sum of the absolute values of the ANs also converge, then we say that the series of initial consideration converges absolutely. So take sum 1 over n, minus 1 to the n, over n squared, and we had convergence both as an alternating series and as its absolute value series counterpart when all of the terms were positive. Well, let's just call it as it is here. We have absolute convergence in this case. So to put this into words, we would have that sum n equals 1 to infinity minus 1 to the n over n squared converges absolutely, because both the alternating series and the corresponding positive term series converge. On the other hand, if a series converges, but when you take the absolute values of the terms and look at the corresponding positive term series, if that diverges, well then we say the original series of interest converges conditionally. I like to think it as being conditional upon all of the negative signs being in that alternating series. Because you take all the negative signs in that alternating series and you turn them into plus signs and you lose your convergence. So the convergence is in effect conditional upon all of the negative signs being there. And with this in mind, then we can identify that the sum n equals 1 to infinity of minus 1 to the n over n converges conditionally. And it converges conditionally because while, yes, the alternating series converges, the corresponding positive series diverges. And so whenever we talk about absolute convergence and conditional convergence, it is this very subtle distinction between them, taking a series and looking at its absolute value counterpart. Now, just so that we can be clear about where the nature of this term comes from, because absolute convergence seems sort of more profound than conditional convergence. It sounds like this very definitive thing, resolutely using the word absolute. I'm going to pause the video here, sketch up sort of a general argument to sort of anchor the nature of that language, and then, yeah, we'll call it a wrap at that point. But yeah, give me a second to get some more math on the board. All right, so one more mathematical fact to look at to sort of anchor why we would use the term absolute on convergence. Let's say we have a series where the sum of the absolute of the ANs converge. Then, in fact, the sum of the ANs must converge. And so what we're saying here is when you have a series that's absolutely convergent, like, in fact, no matter how you put the plus or the minus signs within the expression, there's no way to put them in there in such a way that the series would diverge. No matter how you put the minus signs in, strip away the absolute values, and the series must converge as well. And the idea here is, okay, assume the absolute series converges. You could note that if for any n here, if you take the absolute value of your term plus the term itself, well, if the term was negative, this sum would be 0. And if the term was positive, this sum would be twice the absolute value. So this inequality holds for all n's, whether the ANs are positive or whether the ANs are negative. The absolute value plus the term is no less than 0 and no greater than twice the absolute value of the term. But now, twice the absolute value series converges, because the absolute value series converges. Multiply every term by 2, you'll just get twice whatever the sum of that convergent series is, which means now we have a positive series term which creates a series which is convergent, and we have these other terms that are lesser than. Well, direct comparison comes into play, right? Because when you have positive term series, you would get monotone convergence occurring on the sequence of partial sums there. And so the sum of the absolute ANs plus AN converge by direct comparison. So now what are we going to do? We're going to take this new series here that we just cooked up, which we know to be convergent, and we are going to add it to another series that we know to be convergent. Take the convergent series of the absolute values and throw a minus sign in front. Well, hey, you'll converge again. Well, so then we take this convergent series and that convergent series we just found by direct comparison. Those two would sum together to converge, because whatever this thing sums to, whatever that thing sums to, would just add together whenever you add together the two convergent series. So the sum of convergent series is convergent. But now when you have a convergent series, you can use the properties of summation to separate across that sum. And when you do, you get minus the sum of the absolute values plus the sum of the absolute values. Hey, those cancel away, which means the sum of the ANs has to converge. So the way that I like to think about this is if you take a series which is converging in terms of absolute values, like sum 1 over n squared, this is what, 1 plus a fourth plus a ninth plus a 16th plus so on and so forth. There is a series that converges if you put absolute values on the terms, because, well, the terms are already all positive. So what can you do here? You could put negatives wherever you want in this series. You could put negatives on every other term. You could put negatives on every term. You could put negatives on every third term or every fourth term, or willy-nilly, however you might. And the series that results when you put negative signs wherever you want must converge as well. And if that's not absolutely convergent, I don't know what is. Throw in negative signs wherever you want, and the series will necessarily converge. So that's why we use the term absolute convergence. We don't use the term absolute convergence lightly here. Yes, the absolute convergence relates to the absolute value, but it also means that the series is so convergent, you can throw negative signs in however you want, and there's no way to throw negative signs in clever enough for the thing to diverge. It will always converge no matter how the negative signs are dropped in. So, well, that definitely highlights a difference between absolute convergence and conditional convergence, because when we talked about conditional convergence, just throw negative signs in, in an alternating fashion, and we saw like the series of the 1 over n's converge as an alternating series but diverge without. So conditional convergence, much more sensitive. Absolute convergence, very convergent. There's no sensitive way to throw in negative signs and make it none. So, well, that's that, and hopefully this helps anchor these ideas.